Swayam Prabha. Digital India. Educated India.
I welcome you all to the session of thermal engineering, and today we shall discuss about the ideal power cycle. Thereafter, we shall see that the ideal power cycle is having a few limitations, and discussing those drawbacks of the ideal power cycle, we shall also discuss about the actual power cycle, and from there you will come to know the need of the actual cycle. So, you know that in the last class we have just introduced about the ideal power cycle, that is the Carnot cycle, right, and we have also discussed that the steam power plants operate on the vapor power cycle, and since Carnot cycle is an ideal cycle, accordingly the ideal vapor power cycle should be the Carnot vapor power cycle. Today we shall discuss about this particular cycle, though well known about this cycle and you have studied about it in thermodynamics course, but for the sake of completeness as well as to discuss about some essential issues in the context of the operation of the steam power plants, and also to highlight why this cycle is not suitable for the practical cycle, we would like to take up this particular aspect. You know that in the last class we have discussed about one important index, quality of the steam power plant, that is specific steam consumption. So, before I go to discuss about the Carnot cycle, let us briefly review that particular term, that is specific steam consumption. Why I would like to discuss this? We have defined this SSC, that is specific steam consumption, that is nothing but the mass flow rate of steam per unit of power developed. So, the definition is mass flow rate of steam per unit kilowatt hour of power developed, and from there we could write SSC equal to 1 by W net kg per kilojoule. So, per unit kilowatt power of developed. So, basically you know that we have to express steam consumption rate or specific steam consumption according to its definition, but SSC is nothing but 1 by W net kilojoule per kg. So, per unit kilojoule power to be developed, the mass flow rate of steam. So, this is nothing but 1 by W net, that is kilowatt second. So, therefore, 3600 by W net So, this is what we can write. Now, if you try to recall in the last class, I have mentioned that the choice of a particular cycle which should be used to compare the performance of the power plant depends on two important aspects. What are those? One is the capital cost or the initial cost of the plant. I mean, we should consider these two aspects while selecting a particular cycle for the comparison of the processes which are there in a power plant. So, one is the capital cost or the initial cost, other one is running cost or the operating cost. So, now just I am writing that selection of cycle, of course thermodynamic cycle, depends on the number one capital or initial cost, number two operating or running cost of the plant. See, now why this SSC is an important index for the quality of the plant, you try to understand. So, you know that this SSC is nothing but 3600 divided by W net kg per kilowatt hour. So, basically if the capital cost is, if the plant size is very high, right, plant size is very high, that means W net should be very high. So, if W net is very high, so basically you know that this SSC governs the capital cost by how? If W net is very high, then m dot, that is so you know that higher the specific steam consumption, higher will be the operating cost, higher will be the capital cost. So, what we can see that higher the SSC, higher will be the capital cost, right. Now, if W net is also very less, so higher the SSC, higher, then we have understood that capital cost will be high, right, is not it. So, higher the SSC, that is greater is the plant of the size, capital cost will be high, that is initial cost. Higher this, again I am telling, higher the specific steam consumption, greater will be the size of the plant, higher will be the capital cost. For higher the SSC, you know that W net shall be, W net will be less. So, if W net is less, then you know we have seen that thermal efficiency is W net by Q in. So, for the given heat input, rather given energy input in the form of heat, if we get less work output, then efficiency will be reduced. So, for higher the SSC, greater will be the size of the plant, capital cost will be higher. On the other hand, to have higher SSC, you can see from this expression that W net should be less. If W net is less, for a given input, heat input, efficiency of the plant will be reduced. So, the operating cost or running cost will be high. So, again we can understand from this. So, W net will be less, which in turn will reduce the thermal efficiency of the plant. Okay. So, that is why this specific steam consumption is an important index for the quality of the steam, right. So, that you can understand, because thermal efficiency is nothing but 1 minus W net by Q in. So, if W net is less for a given Q in, then efficiency will be reduced. Okay. So, now with this next we go to the Carnot cycle. Just briefly I am telling, I told you that Carnot cycle for the control mass system you have studied in thermodynamics, that you can imagine that a gas in a piston cylinder upon receiving heat is slowly expanding, and if we assume that the temperature of the boundary through which heat is supplied to the gas is remaining same, then you can assume that the process is isothermal, and that too if the process is very slow process, and if we do not consider the external irreversibilities, right, rather no external irreversibility is there is no heat transfer. So, we can assume that this is reversible adiabatic expansion. Similar way, if we also reduce the temperature of the gas, and I mean there are two different cases. First of all, if we consider that this is a cylinder and this is the piston, and we assume that that, so this is piston is moving up, so slow expansion. This expansion is possible, rather this expansion of the gas can be made possible upon supplying heat from the external source. So, if we supply heat to this gas, say from one temperature reservoir, this is TH and this is say temperature of this particular surface through over which heat transfer takes place is TH minus DTH, and this is QH amount of heat is being supplied. So, in that case we can consider that the expansion is slow. So, you know that of course, the gas will expand and the temperature, pressure and volume of the gas will not will no longer remain in its initial state. So, basically that is the slow expansion. So, we can assume that the process is reversible isothermal expansion. So, that is reversible isothermal expansion we can assume. So, in this case we can assume, so this is this is reversible adiabatic expansion, right. So, there is no heat loss. So, some amount of heat is being supplied to the gas and gas is slowly expanding. So, this is reversible adiabatic expansion, there is no heat interaction between system and surroundings. So, no external irreversibility. So, reversible plus adiabatic expansion. In this case, this is reversible plus isothermal expansion. Why? Isothermal expansion reversible, so basically slow expansion. So, basically this expansion takes place due to infinitesimal temperature difference. So, basically the heat is being supplied from this higher temperature reservoir to the gas through the boundary surface or through the boundary wall, and the temperature of the surface through which heat is supplied or which is transferred from this reservoir to the gas is remaining same. So, the temperature of the boundary is remaining same, and that is T minus dTH. So, this is somehow maintained to be constant. Okay. In this case we can assume that the process is reversible isothermal expansion process. Slow process, heat transfer is very due to infinitesimal temperature difference, and the process is reversible isothermal process. Similar way you also can assume that that heat will be supplied from the gas to the another source. So, this is the these two process we have discussed. Now, also we can discuss like this. Say we have this is the so you know that heat is transferred from the gas to the reservoir, and temperature of this particular surface through which heat transfer takes place is TL plus dTL, and also maintained at constant. Okay. And this is reversible plus, so this is reversible plus isothermal, this is reversible isothermal heat rejection, isothermal heat rejection. I should say that this is not isothermal expansion to be precise. Let us say for the time being we are writing this is isothermal heat addition. So, we are supplying heat to the gas through the surface, and the surface temperature is maintained at Th minus dTh, and this heat transfer takes place due to infinitesimal temperature difference, and the process is reversible isothermal heat addition, slow process, infinite slow process. Upon receiving that amount of heat, if cylinder expands slowly, very slowly, and there is no heat leakage from the walls or through the walls of the cylinder, then this is reversible plus adiabatic expansion. Why adiabatic expansion? Because Q equal to 0 in this particular case. Okay. So, this is I am writing, this is the case, right. And for this particular case you can see is that this is also the case, that is reversible isothermal heat rejection, right. Now, if we also can assume that another process, that is so this is also insulated. So, this is not insulated. So, this is not insulated. Okay. Let me erase it. Not insulated. Here, but the surface is insulated. So, this is gas, this is also gas, and this is also slow compression. Reason is simple. Say suppose we are this is reversible isothermal heat rejection, and if we reduce the temperature of the gas by taking certain amount of heat away from the system, and then the piston, if we assume that the piston is moving in very slowly, again slow piston movement. Okay. So, this is again the process is reversible, that is simple compressible pure substance, which is, if we assume that this is simple compressible pure substance, and if the movement of the piston is very slow, so that is reversible plus adiabatic compression. Right. So, this is adiabatic compression. So, you know that this is the expansion reversible adiabatic expansion, in this particular case the temperature, pressure and volume of the gas will no longer remain at the initial state. So, PVT will change. So, basically so this is the concept of the Carnot cycle for the control mass system. So, this is the control mass system. Control mass system, at least that is the Carnot cycle. If we imagine that, okay, fine, this is the cylinder which contains gas, piston cylinder arrangement, will supply heat and that is reversible isothermal heat addition, will allow gas to expand slowly and it will follow the reversible adiabatic expansion, because the if we insolute the surface, the same cylinder, if we insolute the surfaces, then there will not be no leakage of heat from the system to the surroundings. What we can do next? We can the same cylinder, but now we remove the insolution, we can take certain amount of heat away from the system by connecting one thermal reservoir, and we are maintaining that the temperature of the boundary through which heat will be transferred from the gas to the temperature reservoir is constant, that is TL plus dTL, and this heat exchange will take place through this infinitesimal temperature difference, and so process is reversible, but isothermal heat rejection. Why heat rejection? Because heat is getting rejected from the system to the surrounding. Process is reversible because very slow process, and isothermal. So, basically the temperature is maintained constant of the boundary at which heat transferred, heat is transferred from the system to the surroundings. And next, if we remove this reservoir and if we allow, so basically what will happen? Know that the slow expansion will slow compression. So, basically what will happen? If we take a certain amount of heat from the gas, then piston will come down. So, basically as if the gas is getting compressed. So, if we now remove this particular arrangement and the continuous movement of the piston towards the bottom of the piston will continue, will be there, and this is basically if the movement of the piston is very slow. So, it is nothing but the compression. So, movement is very slow. So, reversible. Now, what is done? Surfaces are insulated. So, there will not be no heat leakage or heat interaction. So, between system and surroundings. So, reversible adiabatic compression. So, imagine all these 4 processes are constituting to form a cycle, and that cycle is the Carnot cycle, but mind it is for a control mass system, there is no flow. So, the concept is like this: if we can now think of a cycle for a flow process, so that would be, rather we are trying to apply whatever we have learned those for a flow process. So, this is basically Carnot cycle, which is having 2 isothermal processes and 2 adiabatic processes. So, 2 reversible adiabatic processes, reversible adiabatic expansion, reversible adiabatic compression. So, 2 reversible processes, one is, so 2 reversible adiabatic processes and another 2 reversible isothermal processes. Okay. So, we are having total 4 processes. Out of these 4 processes, 2 are reversible adiabatic processes and another 2 are reversible isothermal processes. So, all these 4 processes constitute this Carnot cycle for the control mass system. Carnot cycle, if we can conceptualize such an ideal cycle for the flow system, for a flow process, that would be the Carnot cycle for the flow process, and that is a hypothetical power plant which will operate on using this cycle. So, now we are going to discuss about Carnot cycle for a flow process or for the flow processes. Okay, for the flow process, and this is nothing but a hypothetical power plant, a hypothetical power plant operates on the Carnot cycle, operates on the Carnot cycle, right. So, this is the case. A hypothetical power plant operates on the Carnot cycle. So, now what we have seen? We have discussed about a few, rather 4 major component. So, I have discussed about the Carnot cycle, the last example that I have illustrated only to make you understand that the Carnot cycle is essential and ideal cycle, and this is for the control mass system. So, all these processes we can, I mean, if we would like to, if we try to conceptualize all these 4 processes, but for all these processes, but for a flow system, then we will get the Carnot cycle for the flow process, and a hypothetical power plant will be, rather a hypothetical power plant can be operated by using this Carnot cycle. So, now let us draw the schematic depiction of the power plant. So, this is boiler and this is turbine, this is pump, so this is condenser. And this is a cycle. So, all processes are getting executed in a cyclic manner. So, you know that is Q in, that is Q heat addition, that is W in, that is W out, and that is Q out. Okay. So, now our objective, because as I told you that to this power plants operates on this vapor power cycle, but we shall definitely go to discuss about the actual power cycle, which can be used to predict the performance of the plant by calculating the by mapping all the processes in thermodynamic coordinate diagram, and then by calculating the performance or efficiency of all the individual processes. But I told you that ideal cycle, though it is very difficult to achieve in practice, but we need to study it, and in the context of this discussion we also introduced one definition that is known as efficiency ratio or relative efficiency. So, this is an important measure of the performance of the actual power cycle. So, in actual power cycle we can understand that efficiency will not be 100%, and that is not possible at all, but our objective should be to increase the efficiency of the actual cycle so as to reach closer to the ideal one, and that is why the ideal cycle is important to be discussed. So, so basically whatever we have learned from the previous discussion, that is all these 4 processes. So, now what we can see, heat is being added in the boiler, and then it expands in the turbine, and then it is coming to the condenser, wherein by rejecting heat the working substance changes its phase, and that liquid is again taken back to the boiler. So, now question is, I have written P stands for pump, that is we have discussed in the last class. So, today I should not write it pump. So, I am writing it is compressor. C I have used for to denote condenser, so I am writing compressor COM. So, you know that I can arrange it in a bit different way. Let us do that. So, I am writing this is compressor and this is boiler. And then it is expanding in the turbine, this is expanding in the turbine, and thereafter, so this is turbine, and after doing certain amount of work, it is again coming to another device, that is condenser. So, this is condenser and it is rejecting heat to another reservoir, say this is TL, and then this condensate is taken to this compressor to be compressed back to the boiler at the boiler pressure. So, this is what I can see. Now, I can use different symbol for this particular case. So, fine. So, now the compression. So, this is, you know, that this is I can use this color. So, this is the surface of this particular device through which heat is added. This is the surface of this particular device through which heat is rejected. So, this is the surface of this condenser through which heat is rejected to this low temperature thermal reservoir. So, you know, and this is work producing device. So, this is W out, okay. And if I try to show this compressor using, you know, so I am using now, I am using different so compressor, and this compressor is absorbing W in, okay. And this is a cyclic process, and we did not show that this device receive QH from this high temperature thermal reservoir and reject QL to the low temperature thermal reservoir. So, the concept is you do not look at the schematic which I have drawn here at this right panel, the right panel. So, what you can see from this schematic which is shown at the left panel, this is basically the schematic of the power plant, that is also, but the concept is upon receiving certain amount of it, the working substance will change its phase, and that after conversion of the working substance, you know, phase conversion, that substance will be taken to another mechanical device in which it will expand and it does work on the rotating part of this device. And again that working substance is taken to another mechanical device wherein by, you know, certain arrangement it rejects heat to the surroundings, and that is again, and after rejecting heat again its phase will be changed, and finally that substance is again, you know, compressed back to the boiler. So, the concept is taken over here. So, we are compressing. So, what I am writing? So, this is 2, this is 1, this is 4, sorry, this is 3, this is 4. So, this is not the 4. Okay. So, this is what I can see. What is done? So, upon receiving work input from the external source, the working substance will be compressed back to the boiler, wherein upon receiving heat from this external thermal reservoir. So, the temperature of this thermal reservoir is TH minus DTH. Exactly what we have shown over here, the temperature of the surface through which heat is supplied to the gas is TH minus DTH. So, that is, so we are supplying heat from this high temperature thermal reservoir to this device through this surface where the temperature is dTH minus dTH, and we are maintaining the temperature to be constant during the process. And then the working substance upon receiving the heat will change its phase, and when for this particular cycle working substance is water and steam, and when steam is coming out from boiler it will expand and it does work, and when the after doing work, when steam is taken back to the condenser, as we have discussed that it is very difficult to extract, the enthalpy at state point 3 is very high than the enthalpy at state point 4, and it is because of this reason you are getting work output W out. Okay. But still enthalpy at state point 4 is sufficiently high that it cannot be directly, I mean it can be taken to another device for the rejection of heat. You know that if you would like to have complete, we cannot, that is what we have seen from second law of thermodynamics. So, there must be a place, there must be a provision of heat rejection of the working substance. So, it is taken to the condenser, and through the condenser heat is taken to the, so heat is taken away from the working substance through this bounding surface where temperature is TL plus dTL, and we are assuming that the temperature is maintained at TL plus dTL and heat is getting transferred from the flowing steam to the to the surroundings, and again it is compressed back to this device, compressed back to the boiler. So, now you may ask me a question, because okay fine, by we can try to use or utilize all the enthalpy which is there in a turbine, but again in that case what will happen, that we do not require this condenser. It is very difficult, because in that case you need a turbine of very length of the turbine should be abnormally very high, and that would not be possible physically. So, there must be, so that is the problem from mechanical point of view, mechanical operation point of view. So, now, so this is the case. So, we can go one step further. So, we can see that this is compression process, and that the surface of the compressor, surfaces of the compressor are insulated, surfaces of the turbine are also insulated. If the surfaces are insulated, so we can assume that the process is, and if the process is very slow, we can assume that the process is reversible adiabatic compression. Here that heat transfer takes place due to infinitesimal temperature difference, and if we assume that the process is very slow, so reversible isothermal heat addition, right. Here also it is expansion, but the expansion takes place slowly. So, it is assumed that the process is reversible internally, and also there is no heat loss from this turbine to the surroundings. So, it is reversible adiabatic process. Finally, the steam, when it is coming to condenser, we are maintaining the temperature of the condenser, temperature of the surface of the condenser is dTL plus dTL, through which heat is transferred, and if the process is very slow and we are assuming that this is the temperature is maintaining at the temperature is same during the process. So, this is reversible isothermal process. So, exactly all the processes that we have discussed in the context of the control mass system, we can visualize, we can conceptualize all the processes even for a flow system. So, this is the Carnot cycle for a flow system, and a hypothetical power plant will operate using this cycle. Why hypothetical, we will be discussing soon. So, we can go one step further and we can reduce this, we can write, we can draw the schematic again in a in another form. So, we can write that. So, what we can see from this particular schematic is that we are supplying W in to the compressor, we are getting W out from the turbine. So, basically there will be a net work output from this cyclic process. So, all the processes are getting executed in a cyclic manner. So, through this cycle, for a given for a particular cycle, we are getting net work output at the cost of the heat addition over here and heat rejection over here. So, we can reduce that like this, that this is the TH and all the processes are getting executed in a cyclic manner, and we are assuming that this is the surface where temperature is TH minus dTH, and we are getting W net. Of course, to get this W net, there must be a provision of heat rejection. So, that is QL, this is QH, or we can write small QL, no matter, we can write this is QH, QL and this is TL. Okay. And we are assuming that the temperature of the surface through which heat is taken away from this system is TL minus plus dTL. Okay. So, basically if we look at carefully, so for a in a particular cycle we are getting net work output while exchanging heat between these two temperature thermal reservoir, and that is what we have tried to represent over here. So, we are getting net work output while exchanging heat between two different temperature thermal reservoir. So, that is what is that second law, that is it is impossible to construct a thermodynamic device which will operate in a cycle, and the net effect would be work, or net effect would be to produce work continuously while exchanging heat with a single temperature thermal reservoir. So, that is not possible. So, if we would like to get this W net in a cyclic manner, that is what the symbol indicates, there must be a provision of heat rejection. So, this is how the Carnot cycle. Now, again we need to map the processes of the Carnot cycle in thermodynamic plane. So, TS plane, why TS plane? There are many such thermodynamic coordinate diagram like TS, HS, PV, PT, TV, all those. So, why what special here what is special about this TS diagram? Because you have studied from thermodynamics that if we can identify any process and if we can map the process in TS plane, the area under the process line in TS diagram will give you the heat transfer for the reversible processes. Okay. So, so if we try to represent the processes, so so this is TL, this is TH, and if we go to the slide, so that now we are looking at the schematic which is shown in this panel, that is right panel. So, 1 to 2, that is compression process, right. So, if we try to map, so this is 1, this is 2, process 1 to 2. So, that is the compression process, and we need to supply work into the compressor for its smooth operation. So, W in, if we try to write in the specific form, that is nothing but minus H1 minus H2. From where we can write this expression, that in the last to last class I have discussed about the application of combined first and second law to the steady state steady flow processes. We assume, if we assume that the process which is there inside the compressor is steady state steady flow process, and if we apply first law for the flow process, we know that this is not a heat interacting device, because surfaces of the compressor are insulated. So, there is no heat loss from the system to the surroundings, if we assume that this is the system. So, in that case you assume that this is not a heat interacting device, rather this is a work interacting device, because it absorb work for its operation. So, this is also called as work absorbing device. So, compressor so this is COM, this compressor, that is work absorbing device. Work interacting device, it is better to call. Okay. So, this is H1 minus H2. Why negative? This negative sign indicates that this device consumes work. So, this work is not produced, rather this device consumes work. So, that is why this is negative. So, H1 minus H2. Now, what about this process 2 to 3? 2 to 3 is, you know that 2 to 3 is the process that is heat addition, and we have assumed that the process is isothermal heat addition. So, because temperature is maintained at constant. So, this is constant during the process. So, this is also constant during the process. So, you know that is isothermal, reversible isothermal heat addition. So, process 2 to 3, process 2 to 3, that is Q in, that is QH, we can write in the specific form again. So, I am not writing per unit mass flow rate if we try to write. So, this is QH, that is H3 minus H2, right. So, this is H3 minus H2, right. So, this is heat addition to the system. So, you know that next is, so this is work consuming device, this is the this device consumes work, so that is why negative. So, this is the process that is heat addition, and that is, you know, I am writing this process is reversible adiabatic compression, and this process is reversible isothermal heat addition process. Okay. So, you know, and 3 to 4 is again you can understand that is expansion process, but it takes place reversibly because process is very slow, but there is no heat interaction between the device and the surroundings. So, it is again work producing device, and we can map this process is 3 to 4. So, 3 to 4, process 3 to 4, so that W out equal to H3 minus H4, and the process is reversible adiabatic expansion, and finally process 4 to 1. So, you know that this is basically reversible adiabatic expansion. So, we will be getting W out, and that W out we can get from the, you know, application of first law, from the first law applied to the flow process, rather steady state steady flow process. And 4 to 1 you can understand that is again heat rejection, but it is at constant temperature, because the surface through which heat transfer takes heat exchange takes place is remaining constant at TL plus DTL during the process. So, this is, and the process is very slow because heat transfer takes place due to infinitesimal temperature difference. So, that is why this is hypothetical. In reality, it is very difficult to ensure that the heat transfer will take place due to infinitesimal temperature difference both inside the both at the condenser as well as at the boiler. So, that is why the word hypothetical came into the picture and it is written over here. So, this is 4 to 1, that is Q out equal to, here also I will write something, you know. So, this is minus H4 minus H1. So, this negative sign again because heat is rejected from the system. So, that is why, and this is again reversible isothermal heat rejection. So, this is reverse isothermal heat rejection. So, you know that we could identify 4 different processes from this particular cycle, and this is known as Carnot cycle. So, this is the ideal vapor power cycle, that is the Carnot cycle, but you know we have identified. So, basically you know that we have discussed about that heat addition to the system is positive and heat taken away from the system is negative, that is why this is coming. So, this is the amount of heat which is taken away from the system, that is why the negative sign is coming. Similarly, work extracted from the system is taken to be positive, that is the sign convention, but this is the work which is added to the system, that is why it is coming as negative. Okay. So, you know that we have discussed about, at least we have identified all these 4 processes, we could map all these 4 processes in TS plane for the though the points 2 and 3 which are shown on the saturated liquid line and saturated vapor line. So, this is saturated liquid line and this is saturated vapor line. Okay. So, though points 2 and 3 are shown on the saturated liquid line and saturated vapor line, but these two, for the generality, these 2 points could be shown to be inside the vapor dome. Okay. And so, with this, basically if we like to summarize today's discussion, that we have tried to discuss about we have tried to understand the Carnot cycle starting from the control mass system, then we have extended our concept to the flow system, and then we have tried to compare the processes which are there in a power plant using this Carnot cycle, and we could identify all the processes, and we have mapped all these processes in TS plane. From there we have quantified the mathematical expression of the heat which is added to the system or which is taken away from the system. Similarly, the work which is added to the system and work which is extracted from the system. From this, next what we can do, we can at least try to frame the efficiency following this efficiency of the plant following this Carnot cycle, and then we will see what are the drawbacks associated with this cycle. So, with this I stop here today, and we shall continue our discussion on this particular aspect in the next class. Thank you.